And we are pleased to have Leonardo Maltoni back. He's going to talk about representations of UQ of G.
Thank you for the introduction. So before we start, I wanted to make a comment about last time that I forgot. So last time we didn't make any assumption on the characteristic of the field, but in the book by Janssen in chapter 4, he says that it's convenient to assume that the characteristic is different from 2 and also from 3 if the root system has a component of type G2. So I didn't really understand why he makes this assumption, because I believe that the assumption on the powers of Q is sufficient, but I'm sure that I'm missing something. So maybe someone in the audience has a precise answer, but so to be cautious, maybe we should have assumed that the characteristic is not 2 or 3. So if no one has something to say about that, I can move to representation. So as Vanya was saying, today we'll be talking about representations of the quantized enveloping algebra that we introduced last time. So today our field, so here it is important, so it is convenient. We'll assume that the characteristic is not 2, and at the end of the talk, we will also assume that the characteristic is 0. And today, Q will be a unit in the field, which is not a root of unity. Okay, so U will denote the quantized enveloping algebra from last time. And we are interested in U modules. So M will denote a U module. So we want to introduce a notion of decomposition of weight spaces, like in the classical case, as in the classical case. So in this case, we have taken into account some signs. So let me define M lambda sigma, where lambda is a weight and sigma is a homomorphism of abelian group from the root lattice to plus minus 1. So this space is the subspace of M of vectors where the Cartan part acts semi-simply. So so X by an eigenvalue, which is sigma mu times a power of Q given by lambda mu times M. So as I mentioned here, we do not just take into account weights, but also this sign function. And this first part of the talk will be devoted to how to work with it. So how to get rid of it in some sense. So the proposition is that any finite dimensional U module M decomposes as the sum of these weight spaces over lambda and sigma and lambda sigma. And furthermore, we can say how the alphas act on these weight spaces. Oh, that's a sigma. So it sends M lambda sigma into M lambda plus alpha sigma, and the F acts in the opposite way. So M lambda sigma to M lambda minus alpha sigma. And the proof of this is left as an exercise. So this uses the SL2 cases, the SL2 case. Okay, So let me denote M sigma to be the sum of all those weight spaces of type of sign sigma. So inside M. So it is immediate from the proposition, and then M is the direct sum of those M sigmas. Now, we say that a module M is of type sigma if it is equal to its sigma part, so this M sigma. So it only has weight spaces of sign sigma. And the remark is that if we take two modules of different type, then the homomorphism between them of U modules is just 0. So homomorphism of U modules between N and N, if N M is of type sigma and N of type, say, tau, with sigma different from tau, this is 0. And this is very easy to check. You only have to remark that the decomposition is preserved by the action of a morphism, and then this has to be 0. Okay, so what we have said is resumable in the following statement. So if U mod denotes the category of finite dimensional U modules, and U mod sigma is the category, the subcategory, so the full subcategory of modules of type sigma, then we said that U mod is the direct sum of those U mod sigma. Okay, so now we want to describe how we can restrict ourselves to type 1 module. So the ones with trivial sign. So the next remark is that we have equivalence between U mod 1, so those with sign 1 everywhere, and U mod sigma for any sigma. And this equivalence is given, so actually it is an isomorphism of categories, is given by the twisting by an automorphism of the algebra U, which is just given by some signs. So E alpha is sent to sigma alpha E alpha, F alpha to F alpha itself, and K alpha to sigma alpha K alpha. So it's easy to check that this is an automorphism of U. Obviously, we have sigma squared is the identity, and twisting by that automorphism gives the desired functor. So the punchline is that for the structure that we have introduced so far, we can restrict to this subcategory. And we will denote, so for M of type 1, M lambda will be M lambda 1. And next we will see that also with the structure that we are gonna add to the category, that subcategory is stable, but we will see that. So are there any questions so far?
I also think of this equivalence in the remark as tensoring with like one-dimensional representation.
Sorry, can you repeat?
I was asking if I can think of the isomorphism in the remark as being given by tensoring with this one-dimensional representation. Where...
Oh, yes, you can. Yes, I think there is, a way to describe it as tensoring with a one-dimensional representation that take into account the sign. Yes, so it's the, so I don't remember exactly what.
It's essentially the only one-dimensional representation in this category U mod sigma.
Oh, yes.
So where E's and F's act by 0 and K's act by signs.
Exactly. Thanks. So if there are no more questions, then now we are introducing the structure that I promised. So last time we saw that U has a Hopf algebra structure, and this allows us to add structure to the category of U modules. So in particular, we want to give it a monomial structure. So M tensor N, where M and N are U modules, is naturally a U tensor U module. So this is true in general. And via our co-multiplication, this is a U module. And so what I said is that that subcategory U mod 1 is stable under tensor product. So the remark is that if we take, so these are still general U modules. If we take M lambda sigma and tensor it with N mu tau, so this is inside M tensor N of weight lambda plus mu and sine sigma tau. So in particular, if we take sigma and tau to be 1, we get into the sine 1 part. So U mod 1 is stable under tensor product. The second important remark is that, so this is important, the usual canonical isomorphism between these two vector spaces is not U-linear in general. And this is because, as someone mentioned last time, the co-multiplication is not co-commutative. So remember, for example, that delta E alpha was E alpha tensor 1 plus K alpha tensor E alpha, and etc. So this is not invariant by switching the factors. And this is important because there exists morphism of U modules from M tensor N and N tensor M, and this will be, I think, the topic of next lecture, or maybe the next one, so the following one.
The one after the next.
Okay, and these are called R matrices. Okay. So as I said, we have additional structure via the Hopf algebra structure of U, and this is not just the tensor product, but also we have a trivial module. So remember, we had the co-unit from U to K, a morphism of algebras, and this gives K the structure of U module via U x equals epsilon U x. So this is a scalar, and we can just multiply. And this is called the trivial module. Then we have the antipode, so that anti-automorphism of the algebra, which allows to give to the dual of a module the structure of a U module. And how? So if we have a map inside the dual and we want to apply U to that, then the image of this new map over a vector M will be given by f of S of U applied to M. So here we use the antipode. And more generally, this allows us to give, so more generally, we can give to these spaces, to this space, the home from between two modules as vector spaces, the structure of a U module, because this is isomorphic as a vector space to n tensor M dual, and we have all the ingredient to make this one a U module, and we make this one a U module via this isomorphism. So there is something to be cautious with. So the order of n and m dual is important. So we said that we cannot just switch factors as with vector spaces. So here is important that n appears first. And then in the remarks that I will make, this will be, I think, clearer. So, okay, and then let me make this, also state these properties and remarks. So the first one is that the canonical morphism that we have from M to the double dual, sending a vector to the map associating the operator f to f of m, which is an isomorphism of vector spaces if M is finite dimensional, is not U-linear. Because you can check that here you have to deal with the square of S, and the square of S is not the identity as we have seen last time, and we described it. It was the conjugation by k minus 2 rho. So we can fix this problem, and we can slightly modify this morphism to get a morphism of U module. So if we take this one, this is one. So this is a morphism of U modules, and it is an isomorphism if M is finite dimensional. The second remark is that, so usually you have the morphism M dual tensor M to K, sending F tensor M to F of M. And this is U-linear, so this is a morphism of U modules. But we cannot already interpret it as the trace, because we said that, so the endomorphism space of M should be identified with M tensor M dual. And if we take M tensor M dual to K with the same definition, then this is not U-linear by the same problem as before. But we can use remark 1, so we can build a a unilinear morphism from this space to that space via the identification of M with the double dual, and then we go to K via the first morphism applied to M dual. But in this path, we have to use this morphism, so this twisting by K minus 2 rho. So in the end, what we do is taking M tensor F to M F of K 2 rho minus 1 M. And if one identifies this with the endomorphism space of M via, so by definition, this takes the map phi to the trace of phi after K 2 rho minus 1. And this is called the quantum trace. So the things I am introducing, so this dual and these properties of maps between M dual tensor M to the trivial and M tensor M dual to the trivial can be summarized by saying that the category U mod is a rigid monoidal category, but I won't get into these details. And yes, I didn't say that. So I can make a third remark. So if I take the weight space lambda sigma of the dual of a module, this is the subspace of the dual, so functions that takes all weight spaces of M to 0 if lambda prime sigma prime is different from minus lambda sigma. And so this is just to say that U mod 1 is also stable by taking the duals. So it is a rigid monoidal subcategory. Okay. So stable. The fourth thing I want to say is that so given any module, we can define the subspace of invariance. So it is given by those vectors over which any element of the algebra acts by the scalar given by the trivial module. And the remark is that if we take the space of invariance of this module, then this is just the subspace of morphisms of U modules between M and N. And this is, again, not difficult to check. And final thing is that the usual homomorphism between this space of morphisms from M to hom NV, where M, N, and V are U modules. So the usual one to the morphism space from the tensor to V. This is U linear. And by remark 4, this implies that also the invariance subspaces are preserved, and so we can write U instead of K. Okay, so this finishes the this description of the structure of this rigid monoidal category. So are there any questions?
Yeah, maybe a quick comment. So actually what you talked about is more than just a rigid monoidal category. This is what is called the pivotal category, where you have a tensor isomorphism from X to X double dual. In a general rigid category, they may be non-isomorphic. Okay. And so, but in a general rigid category, you can still define trace, but it would not be trace of a morphism from X to itself, but from of a morphism from X to X double dual.
Okay. Thanks. So, sorry?
Just a question to Pavel, why is it called pivotal?
I don't know.
So to move on, now we pass to the first interesting part of this. So the first part regarding representations of, so structural theorems of representation of U modules of U, which is the classification of simple finite dimensional U modules. So this is very similar to the classical case, and here we restrict to type 1 U modules. So let me start by the lemma, this lemma, that resumes some properties that will be useful. So the first one is, so let us fix, after all, before, so the beginning, M, a finite dimensional U module. Then we have a first property, which is that there exists a lambda weight, and so there is a question maybe in the chat.
Well, there was more follow up on Pavel's.
Yeah. So Roman is asking, are there meaningful examples when fourth dual of X is isomorphic to X, but X double dual may not be isomorphic to X? I think so, but I have to think about it.
How about we discuss it during the break?
Yeah.
This and a countable number of questions of the same kind.
So what I was saying, so yes, so there exists a weight and a vector of weight lambda, such that all E alphas act as 0 over V. So this is what corresponds to highest weight vector in the classical case. And if M is finite dimensional, then the lemma assures that there exists at least one. Secondly, if lambda and V are as in A, then lambda is dominant. And we can check that if we apply F alpha, this number of times, so lambda alpha check plus 1 times to V, we get 0. And let me add a third part to this lemma, is that, so M is finite dimensional, we can check the usual property that the dimension of the weight space of weight mu is always the same as, so it's invariant by the while group. So if you apply, if you check the dimension of MW mu, this is the same for any W in the while group. And the proof of this is really just as in the classical case. Okay, so the fundamental tool that we will be using for studying simple finite dimensional modules is as in the classical case, the Verma modules. So this, so take lambda a weight. The Verma module is defined as the quotient of the algebra U by the ideal generated, so the left ideal generated by the E alphas, and these expressions K alpha minus Q to the lambda alpha. So there is, okay. And so so this is constructed in a way such that the class of the unit that we will call V lambda, this is a highest weight vector. So E is as in A of the lemma. And the properties of these Verma modules are, so the first one is that there is an isomorphism of vector space, but actually of U minus modules between U minus itself and M lambda, sending Y to Y V lambda, which is the same thing as the class of Y. And this allows us to, will allow us to describe basis of M lambda by basis of U minus. So secondly, we have the usual universal property of the Verma, which is that if a vector inside a module is a highest weight vector, in the sense of lemma A, then there exists a unique morphism from M lambda to M, sending the generating vector of M lambda to V. And finally, we have, as in the classical case, that M lambda has a unique simple quotient, L lambda, and we have that the endomorphism space of M lambda as a U module, as well as the one of L lambda, is just given by scalars. So it's reduced to scalars. So let me check.
All right. I have a question for the audience. Well, a lambda is a simple module, so it would seem that the last equality just follows from the Schur lemma. Is it the case?
Can you repeat your question, Ivan?
The question was addressed to younger members of the audience, sorry, Rafael, and it asked whether the last equality follows from the Schur lemma.
I forget, Ivan, I forget what the assumption on K was.
That's the right answer. So we never assumed that K is algebraically closed. So we cannot really use the Schur lemma for that. But this equality is actually quite easy. So it is left as an exercise.
So the next thing I want to say is, as Vanny was saying, here we're not assuming that K is algebraically closed, and also we're not assuming that K is characteristic 0 for the moment. And next proposition
excuse me. So,
yes.
but it's very important to emphasize that we use that Q is not a root of unity multiple times.
Yes, yes.
Otherwise, the claims of this proposition above are just not true.
Thanks. So the proposition I wanted to state is that so let us take a dominant weight. Then there exist morphisms phi alpha from the Verma of highest weight lambda minus lambda alpha check plus 1 alpha to m lambda. So let me call this lambda prime, sending the highest weight vector L v lambda prime to f alpha to the lambda alpha check plus 1 v lambda. So to check this is easy. You can just use the classical case or check it yourself. But
I think that lambda prime is this whole thing, not just one summand, right?
Yes, sorry. Yes. So thank you. Yes. And okay. And then we can define L tilde lambda to be the quotient of m lambda by all the images of those phi alpha. So the proposition is that, so the first claim is that L lambda is finite dimensional. Secondly, and this is easy, we get from the property of L lambda without the tilde to be the unique simple quotient that it is also a quotient of L tilde lambda. And this implies that it is finite dimensional. And let me say that more generally, so this is a comment, more generally, if M is finite dimensional and has a highest weight vector V of weight lambda, so in the quantum sense, then the morphism given by the universal property from the Verma factors through this L tilde lambda. This just by the lemma. So you have to apply the lemma and you get for free this fact. And the third property is that, as in the classical case, you can check that L tilde lambda satisfies Weil's character formula.
This I am actually not sure about because we haven't established the Poincare-Berghoff-Witt theorem yet. So we don't know the character of U minus.
Okay. So okay, I won't assume this. So it is not.
So this will be true at the end, but we will only establish Poincare-Berghoff-Witt in lecture number 8. Well, I mean, in lecture chapter number 8. Sorry.
Okay. So thank you. So okay, one can do things without this assumption. So this claim. Okay. So am I forgetting something? No, okay, so finally the theorem about the classification of simple finite dimensional U modules is the following. So simple finite dimensional U modules up to isomorphism are labeled, so are parameterized by dominant weight, and the association is just lambda to L lambda. So these are all possible finite dimensional simple U modules. So
do you mean the type 1?
Yes,
like...
that's true. So yes, we are restricting to type 1 modules. So
I lost track. So we've been assuming this whole time that Q is not a root of unity?
So yes, so for the whole lecture, we are assuming that Q is not a root of unity.
Okay, and so this map from L tilde to L is not necessarily an isomorphism?
Sorry, can you repeat?
Is the map from, so you seem to implicitly say that the map from L tilde to L is not necessarily an isomorphism. Is that right?
So yes, that is also, so in general, we will prove that in characteristic 0 case, so not just when Q is not a root of unity, but also when characteristic of K is 0. I'm not sure that if Q is not a root of unity, but the characteristic of K is not 0, if L tilde is the same as L, but
yeah, it is the same, yes.
Okay, so in all characteristics.
But if you yeah.
Okay. Okay, so let me move to some examples. So the first example of a U module that we will make is the one of, so the one which corresponds to the natural representation of SLN. So let G be SLN. So we will build it by hands, but you will see that it corresponds to the natural representation. So consider V finite dimension n module, which is given by a basis V1 to Vn. So here the simple roots are alpha 1, alpha n minus 1, where U acts in the following way. So we have some k alpha I that act on the Vj either via Q, so Q Vj, if j equals I, Q minus 1 Vj if j equals I plus 1, and just Vj otherwise. Then the action of the E alpha is given by Vj minus 1, sorry, if j is I plus 1 and 0 otherwise. And the F alpha is analogous, but in the opposite direction. So Vj plus 1 if j equals I and 0 otherwise. So these are some formulas, and you can check that this defines a U module, but maybe it is not so easy to imagine just by the formulas. So let me show you a picture that resumes all the information that I gave you. So here you have on the top, you can see the basis V1 to Vn, and also this is alpha 1, and all those arrows represent the action of the negative and the positive part. So where you don't have arrow where they are 0. So f alpha 2 only acts on V2 and nowhere else. And the same is true for the E alpha. On the lower part of this diagram, you have a representation of the action of the Cartan part, so the weights. And for example, V1 is a weight vector of weight pi alpha 1, where pi alpha 1 is the fundamental weight. And then you have the weight pi alpha 1 minus alpha 1, which is given by these coefficients, and so on. So this resumes a little bit what I've said in formulas. And the remark is that, as was mentioned last time as a motivation for the definition of U, so if you write down matrices of these Fs or of these Es, these are just the same matrices as in the natural representation of SLN in the classical case. And if you write down matrices of the Ks, then these will be something like 1, 1, Q, Q minus 1, 1, so on. Whereas for the semi-simple algebra, you have 0, 1 minus 1, 0, and so on. And you can see that this matrix is obtained by exponentiating Q to the power this matrix. So that motivation is actually true in this example. And so before the break, let me do another example. So maybe I will just wait a minute here. And so if there's no comment or question, the next example is the analogous of the adjoint representation in type A2. So let G be SL3. And in this case, we have simple roots alpha and beta. And so instead of giving formulas that maybe are like too many expressions, let me just show you to begin the usual representation in the classical case of so the adjoint representation of SL3. So let me just give names. So SL3 will be the span of E alpha plus beta, E alpha, E beta, H alpha, H beta, F alpha, F beta, and F alpha plus beta, where these are the positive part, these are the negative part, so just the nilpotent matrices as usual, and this is the Cartan subalgebra. So this is the basis of the Cartan subalgebra. And here you have the usual adjoint action represented over the algebra itself, but I just chosen some signs for some of the basis vector in order to get the coefficients of the operations are as simple as possible. So where there is no coefficient, it means that the coefficient is 1, and the only two places where the coefficient is 2 is when we apply the adjoint action of E alpha to H alpha or F alpha to the same. And not all arrows are drawn, because if not, the picture would be incomprehensible, but you can guess the missing ones by mirroring the one that are present. And in green, you have the weights of the Cartan subalgebra, as usual. So this is just to have in mind what is the usual adjoint representation. And we want to make a quantum analog of that. So a quantum version. And this is given by the following. So we have an analogous basis, and the action of the positive and negative part, so the E's and the F, is basically the same, but for the coefficient of these two arrows that are not anymore the number 2, but they are quantum 2, so Q plus Q inverse. And about the Cartan part, instead of, so this is just as in the previous example, instead of having 1, 1 and 2 minus 1, we have the corresponding powers of Q, because again, that motivation is still valid. And so this picture represents what I've just said. So this is, I think, a good time to make a break and left this picture on the board.
Maybe also want to make it somewhat larger.
Sorry? It's larger,
you
yes.
may want to
yes.
make it somewhat larger. Good.
Okay.
All right. Are there any questions or comments?
For the duals, would it be useful to distinguish between right and left duals?
So I think so. I think the comment of Pavel just a moment ago. So this is so the left dual is still the dual as we defined it, but like you fix the, so if we say that those duals are the left dual, then the structure of right dual is given by the isomorphism from M to the double dual by those. So because fixing the right dual and the left dual means fixing the evaluation and co-evaluation maps, and the evaluation maps are given by those that I gave. And if you want to give the evaluation and co-evaluation for the right dual, then you can still pass through the double dual, and then you have everything you want. So once you fix a particular isomorphism from M to the double dual, then you have fixed the structure of. This is my understanding, but maybe it's better that someone else give an answer.
No, I think that's correct.
Yeah, I think maybe it's more natural to have natural formulas for and then you see exactly when you use a double dual.
Yes, so maybe I can.
And are we going to see like diagrammatic for this kind of thing at some point?
So not in this lecture, but yes, it could be nice to. So there is a diagrammatic for Hopf algebra in. So I know some of that, but I didn't talk about that. So what I was saying is that yes, so to fix the dual, so a left dual, you have to fix this morphism from the M dual tensor M to K, and a co-evaluation from K to M tensor M dual, and these are the natural one. And once you fixed a morphism from the from N to the double dual, you can do like in this case, and fixing automatically the right dual morphisms. So the moral is that for right duals you have to twist by this K2 rho minus 1, and for left dual you don't have to.
Okay, maybe I can pause to resume.
Yes, so let me move to the next slide. So now I want to state an important theorem that will be used, I think, in the next lecture, or yes, already for talking about the center. So this is about this is a structural theorem on U. So if an element inside U annihilates all finite dimensional U modules, then U has to be 0. And so let me give you a sketch of the proof, which is quite technical, so I won't get into all details. So the idea is, so suppose that U is not 0, then write, so let Yj and Xi be bases of the negative part and the positive part, respectively. And as we saw last time, so K mu to be the natural basis of the Cartan part, so the one given by monomials in the K alphas and the K alphas minus 1. And then we can write U as a linear combination over J mu and I of some coefficients times Yj K mu Xi. So we are supposing that it is not 0. So there exists some of those coefficients that are not 0. And we are taking those with Xi of maximal degree. So chose nu 0. So remember that the grading is over Z, so over the root lattice. So choose a nu 0 inside here, maximal, such that there exist J, U, and I with the degree of Xi equal nu 0, and Aj mu I not 0. So at least some of them. Now we consider, so the idea is to consider modules of the form L tilde lambda tensor L tilde lambda prime twisted by omega. So remember that automorphism of the, sorry, this is an omega. That automorphism of the quantized enveloping algebra. So this is finite dimensional, and we know that U acts as 0 over here. In particular, we have a highest weight vector here, V lambda, of weight lambda, and a lowest weight vector, because we are twisting the action, that we will call W lambda prime, which is of weight minus lambda prime. So this. Because also the action of the Cartan is twisted. And we know that U applied to V lambda tensor W lambda prime has to be 0. But then this is sum and this has to be 0. And so over O mu J and I. And we do a remark. So when we apply the monomial Yj K mu Xi to this vector, what do we get? So after some work on the definition of delta, so because we have to apply this element of U to a tensor product, so we have to apply the co-multiplication, one can check that this is equal to some power of Q that we will investigate, times Yj applied to V lambda tensor W lambda prime, so sorry, Xi applied to W lambda prime, plus other terms. And what is important is that this belongs to so L tilde lambda tensor the weight space of L tilde lambda prime twisted of weight minus lambda prime plus the degree of Xi, because we have W lambda prime and we apply Xi to that. And the remaining terms live, so let me call it L tilde lambda without the prime, tensor, L tilde twisted lambda prime of weight lower than minus lambda prime plus the degree of Xi. This is just a consequence of the definition of delta. You can check that this you get this top part and then lower terms. And what is the power of q? So the power of q comes out from the action of this k mu in the middle that acts after xi but before yj, and of all those k's that comes from the definition of delta applied to the xi's and the yj. So we have in the definition of delta that some k's appear. So let us focus on this k mu. So this applies after xi. So in this vector, it will give a power of q given by mu times minus lambda prime plus the degree of xi, which is the weight of xi w lambda prime. And when acting on v lambda, because it acts before yj, we have mu lambda. And then we have all other terms that come from the other k's coming from the delta, but this does not depend on mu. And this is the important fact. So let us just forget about that information. So, okay, and the remark allows us to write this sum, let me call it star. So by the choice of nu 0, which is maximal among those for which some a's are not 0, this sum equal to the sum over all j mu I such that the degree of xi is maximal, so is nu 0, of a j mu I, this power of q the degree is mu 0, so I can write that, plus those terms that I don't write, times yj v lambda tensor xi w lambda prime, plus terms that by the remark are inside this subspace. So lambda twisted, L tilde lambda prime twisted, of weight less than minus lambda prime plus nu 0 by the remark. Okay, so this was the most technical part. And because this has to be 0, then we can project onto this top part and we can deduce that also just this sum has to be 0. Okay, so this has to hold for any lambda and lambda prime in weights, so inside capital lambda. And the idea is that if we take lambda and lambda prime sufficiently large, so sufficiently dominant, then the yj v lambda and so the yj v lambda and the xi w lambda prime appearing in the sum so in this sum are linearly independent. To see this, let me show you a picture that maybe is clearer than words. So this is a picture of our L tilde lambda, and this is the twisted one. So this is an A2 picture. So this is the whole thing is the Verma. And to get the L lambda tilde, so the L tilde lambda, we quotient by those subspace that are images of the phi alphas, that are the Grimm spaces. So what we get is a finite dimensional module, which is the orange part. And with respect to the Verma, there are some weight spaces that are affected by the quotient and other weight spaces. So the top part, this rectangle, so this parallelogram, which are not affected by the quotient because they are higher. And the idea is that if lambda is sufficiently large, then we are operating inside this area. So it is just as working in the Verma. So those vectors are linearly independent. And the same is true for the twisted one. So we are here and here if lambda and lambda prime are sufficiently large. So maybe this is clearer than all formulas.
Maybe
Okay,
it should be said that we had a very similar argument when we established triangular decomposition.
Yes, yes, the argument was similar. Yes, exactly.
And it's important that you pick highest weights in some Zariski dense subset. That's the only thing that was used in that argument. And when we pick lambda and lambda prime large enough, there is no difference between Verma module and its quotient for our purposes. It's just a brief retelling of this argument.
Yes, and thanks. Okay, then by this observation, so this linear independence, so all those tensors appearing in the sum are linearly independent. So we can deduce that for any I and j with the degree of xi equals mu 0, so those appearing in this sum, we have that just the coefficient of that vector, which is the sum over mu in the root lattice of a j mu I q to the mu minus lambda prime plus mu 0 plus mu lambda plus that part that does not depend on mu. So I don't write it down, but this does not depend on mu equals 0. So that part does not depend on mu, and we can get rid of it because it's just a power of q that gets out from the sum and does not affect the vanishing of the remaining part. So we can just forget about that. And okay, now what we are writing down here is actually a linear combination of some characters. So let me be clear about that. What does it mean lambda and lambda prime sufficiently large is that this holds for lambda and lambda prime inside some semi-group lambda plus n, which is the weights inside lambda for which lambda alpha check is sufficiently large, so is greater than this n natural number for all simple roots. So this is a sub-semi-group of this abelian group. And what we are writing there, so let me define chi mu to be the character of this semi-group, defined as, so the one sending lambda to q to the power mu lambda. This is a character of this semi-group. And what we are writing there is that this linear combination of j mu I q mu minus lambda prime plus mu 0 times chi mu is 0, because this has to hold for any lambda inside here. Now, there is a theorem by Artin that says that different characters of a semi-group are linearly independent. So these are different because Q is not a root of unity, so all these powers give different characters. And then this combination being 0 means that all those coefficients are 0. So this is Artin theorem. And that power of Q is non-zero, so that implies that A, J, mu I is 0 for all I, mu, and J with this property, which contradicts the assumption that at least one of them is non-zero. So we have a contradiction. And this concludes the proof of this theorem. So are there any questions?
Yeah. So what Artin theorem about? I mean, is it a special case of just theorem about algebras that you have irreducible representations of algebras? Then they are on algebra. They are always characters of those are linearly independent. Is that a special case of this?
Yes, I think one can see that as a special case of that, but this holds for, you can show it easily for semi-groups, that if you have different characters, so you can show that if any finite number of different characters is a set of linearly independent function over that semi-group, and here we have a countable number of them, but a linear dependence relation would imply only a finite number of them. So this follows from that theorem.
Mm-hmm.
So, okay. Now let me pass to the last part of this talk. So the characteristic zero case. So for this section, we will assume that the characteristic of K is zero. And always that Q is not a root of unity. So the first theorem, which makes the theory in this case similar to the classical case in characteristic zero, is that for lambda dominant, we have that the L lambda tilde is actually isomorphic to the L lambda. So the simple is given by that quotient of the Verb module, and they satisfy Weil's character formula. So actually, I won't give the proof in the general case of Q not a root of unity. I will suppose that so only in the case Q is transcendental, so a little more. Over Q. And so actually I will reduce to a simpler case by this. So I won't give the details of this argument, but one can reduce to the case K equal QV, so the rational fractions of over an indeterminate with V equal, so where Q equal V, by the following remarks. So let me denote, so maybe this is not the right, let me phrase it another way. One can reduce to QV with Q equal V by the following remarks. So let me denote M lambda K to be the Verb module constructed over K, so over the quantized invariant algebra constructed over K, and M lambda QV, the one constructed over QV. So for the moment, K and QV are not necessarily the same, and I'm showing that briefly that one can reduce to the second case. And let me also denote L tilde lambda and L lambda to be the corresponding submodules. And to this side, so it is not difficult to check that so by transcendence of Q, we have a morphism from QV to K, sending V to Q. And then we can tensor, so extend scalars from these vectors to the bigger field, to the extension K. And it is not difficult to check that these first modules are actually the same as the one constructed directly over K. And it is a little more difficult, but still not that much, to show that also the simple one is given by the extension of scalar by the one defined over QV. And this uses some general algebra, for example, Jacobson density theorem, but I won't get too much over that detail. So let us believe that we can just extend scalar from this field and reduce to the case where K equals this field. So let K equals QV. And here the argument is a deformation argument. So let A be the subring of Laurent polynomials over the rationals inside K. And this is a PID. So a principal ideal domain. Now we want to, so let, for brevity, call L lambda just L and L tilde lambda just L tilde. So we have fixed the dominant weight. Now we define LA to be the A submodule of L generated by vectors of the type of the form f alpha 1, f alpha k times v lambda, where v lambda is the highest weight vector. So for all choices of alpha I simple loops. So by finiteness of the dimension of L, there is only a finite number of these that are non-zero, because the weight has to be bounded from below. So this means that LA is a finitely generated A module, which is also torsion free. And hence, by the fact that A is a PID, it is free, actually. And we can make the same construction for L tilde A, replacing L by L tilde. So I won't give details, but we get another module, which is, again, free. And in the same way, we can define LA mu to be the A submodule of LA, we can also say, generated this time by the vectors of that form, but such that the weight of the final vector is mu. So such that lambda minus alpha 1 minus alpha k equals mu. And of course, there is, again, a finite number of them. So this module is, again, finitely generated and free. So it is a free submodule of LA. And the same for LA tilde. Okay, so we have the ingredients, and one can check that the rank over A of these L tilde A mu's is the same as the dimension over K of the L tilde mu's. So the weight spaces of L lambda, L tilde. And the same is true for L, of course. sorry, without the tilde.
This is very easy from construction.
Yes. L mu. Exactly. So, okay. So the next step is use these A module, these free A modules, to construct a complex version of these modules. So let so consider the morphism from QVV inverse, so RA, to C, which sends V to 1. Now we can define LC to be the module that we get from LA tensoring over A with C. And in the same way, we get L tilde C to be L tilde A tensor C. So one can check that the operations of U over these A modules, so of the F's and of the E's and of the K's, gives operation of the Lie algebra, so the classical Lie algebra G, over these two modules. So actually one can just define operators and then check Serre's relations, and one have a G module structure over these two. So one has okay.
So maybe a better way to say is that the operators F and E give the structure.
Yes, that's true. One has that, so LC and L tilde C are G module. So are complex vector spaces, and by this remark, they are G modules. But one can say more. So furthermore, one has, so one LC and L tilde C are simple. And to show that, one shows that they are generated by a highest weight, and that their only simple quotient is and they have only one simple quotient. But then using the structure theorem, so the Weil's theorem for complex semi-simple Lie algebras, one has that these modules have to be semi-simple, and then having only one simple quotient, they have to be simple. So this is briefly the argument that one used for L and for L tilde. So they are both simple. Secondly, we have
maybe, can I add a little bit? So the way how you formally see this action of G, well, you introduce new elements in the quantized universal enveloping algebra. Let's call them H alpha, and they're just this right-hand side in the SL2 relations.
Yes.
And then what you check is that when you specialize Q to 1, the E alphas, H alphas, and F alphas, they satisfy the usual relations. And you also show that the lattice, this L sub A and L tilde sub A, these lattices are stable under these elements. And this is how you get your action.
Yes, exactly. Thanks. So, okay, so we have these simple modules. And the next thing is that if we compute the weight subspaces, so the weight spaces of these modules, they are given by tensoring those A module LA mu over A with C. So this is not immediate, but one can check it rather easily. And the same is true for L tilde. Good. And then what follows is that the rank over A of those LA mu and the rank over A of L tilde A mu, it is just the dimension over C of the weight spaces of this representation, and the same for L tilde C. But then we have that these two representations are simple G modules with the same highest weight. So by the classical theory, they are just the same. And their dimensions of weight space satisfy Weil characters formula. Then we get the claim by the fact that these ranks that are equal to those dimensions are actually just the dimension of our weight space in the original, so in the U module structure. And then because L tilde, so L is a quotient of L tilde, we get the claim. So this concludes the proof in this case of QV, which generalizes to the case Q is transcendental. But one can prove also in the classical, in the general case, Q is not a root of unity. But here we won't do that.
Yes, maybe I can. Do we still have time?
Yes, you can.
So maybe I should make a comment. So if you want to prove these claims in the general case, you need to undertake some study of the category of finite dimensional modules. And what you find in that study is that you have a highest weight category. And this is true outside of root of unity. It's also true at the root of unity case if you arrange things correctly, and we'll talk about that. But then what you can also show is that outside of root of unity, the highest weight category you get is semi-simple. And then you can get the usual business of how you get the Weil character formula when you know the characters of Verma modules, things like
that. Okay. So actually, yeah, I'm not sure you need this highest weight category business and so on. Well, so what you need is, if you recall that proof in the usual Lie algebra case, all you need is the Casimir operator. And then you can write, you can show that the only Verma modules that can occur in the formula for the character are those from the Weil group orbit, and then you're basically done. And so you can do the same thing here. There is something that is called, actually there are a couple of ways, but you have to use the R matrix, which will be defined later. So you can construct the Drinfield's element, which exists in any braided category. And that would be one option for quantum Casimir. Another option is to use the Drinfeld-Reshetikhin construction for the whole center. And then again, the same thing can be done. And all you need is SL2. You need to know that SL2 works the same way as for Lie algebras. And that's easy to show.
Thanks, Pasha.
Yes.
So there is a question in the chat. Do you need complete reducibility to get tilde L? Oh, okay. Okay.
So when Q is transcendental, then we are done by this algebraic argument. And when Q is not a root of unity, then yes, we need to have complete reducibility, as Pavel explained.
Yeah, I don't think, well, you can also show complete reducibility by using the same argument with the center. Actually, it is better not to, I mean, this argument, if you don't want to use R matrix, then you can do this to prove for transcendental Q. But actually, if you have the R matrix, it is easier to just, instead of using the result for Lie algebras, just following the same proof, but in the quantum case. And it will give you proof for every q which is not a root of unity. And moreover, it will tell you for which roots of unity. So for every weight, you will see which roots of unity you have to exclude in order to have the same statement, in order for the character being given by Y character form.
Okay.
Vanya, do you agree?
I think so. I'm not ready to sign the paperwork yet, but I think I'm good.
Mm-hmm.
Okay, perhaps we could continue.
Okay, thank you. So let me then move on. So why it is not?
Actually, I had a question.
Okay.
So I think
Yes.
for the proof, you argued that like when you tensor this Hopf algebra to C, it contains the universal enveloping algebra of G, right?
So it's yes, in some sense. So you don't tensor the algebra with C, but you define this structure over QVV inverse, and then you don't use the original algebra over QV. You use like a QVV inverse structure of that.
Yeah. Okay. That's what I'm talking about. Yeah. So my question is that tensor over A with C, is that actually equal to the universal enveloping algebra of G?
Good question. So
the answer is no, because you still carry case.
Yeah.
No. So you need to tensor not the whole algebra, but with a subalgebra which is generated by E's, F's, and the elements H that Vanya defined, which is Ki minus Ki inverse over Q minus Q inverse. That's a subalgebra. And you have to tensor that, not the whole thing, with C, right?
okay,
Yes. Otherwise,
that
you still
sense.
carry those multiplicative elements.
Right. And if you do this, you will get enveloping algebra.
What elements did you admit in that subalgebra? You said E, F, and what?
And you have to admit elements K alpha minus K alpha inverse divided by Q minus Q inverse.
Which already lie in the subalgebra generated by E's and F's.
Right.
By definition.
But you should not allow K's, Ki by themselves.
Okay, so let us state the last result of this lecture. So yes, before we have, let me state a proposition, which actually is true also in not a characteristic zero case, so in any characteristic. Not two, just for simplicity. So we have that the dual of a simple module of highest weight lambda is, just as in the classical case, the simple module of highest weight minus W0 lambda, where W0 is the longest element of the while group. So I could have stated this theorem before when talking about general properties of simple finite dimensional modules in any characteristic, but I do it now because it will be useful for the next theorem. So the theorem, and this time we get back to our characteristic zero case, is that any finite dimensional module is semi-simple. So this extend the classical result for complex Lie algebras. So let us prove that. And so it is enough to show that any short exact sequence of the form L lambda M L mu splits. Because then we can just take the composition series of M, and if each one of these sequences splits, then we get semi-simplicity. And the first observation is that we can reduce to the case when mu is not less than lambda. Because if mu is less than lambda, then you can just dualize the sequence and you get parenthesis M dual L lambda dual 0. And by the proposition, this is L minus W0 mu, and this is L minus W0 lambda. And this relation is still valid if we apply minus W0. So minus W0 mu is still less than minus W0 lambda. But then we are in the case, because now the role are switched, and minus W0 lambda plays the role of mu, and we have that minus W0 lambda is not less than minus W0 mu, because it is greater, and hence we are in that case. So let us just reduce to that case. Now take V bar inside L mu, so the highest weight, so a non-zero vector in the muth weight space. This is a V. So by surjectivity of pi, so let us call this map pi. There's a question. So it's about so maybe I will answer that after the proof, or try to. Okay, so there exists a V inside M, so actually inside the weight space, the muth weight space, such that pi of V equals V bar. Now we want to consider the module generated by this V inside M. So this is finite dimensional, and we want to show that V is a highest weight vector of weight mu. So we want to show that E alpha V is 0 for all alpha in pi. And this because if some of them is not 0, so if E alpha V is non-zero, then it belongs to the weight space of weight lambda plus alpha, so mu, sorry, plus alpha, which is then non-zero. But then this means that mu plus alpha, so it cannot be a weight inside L mu because it's greater than mu. So it has to be a weight inside L lambda because the sequence is exact and it gives exact sequence also for weight spaces. So if the weight does not appear here, it has to appear here. But then we deduce that mu plus alpha is less than lambda because all, so less than or equal than lambda, because all weights appearing in a lambda have to be less than lambda. But this contradicts this assumption. So we have this relation. And then what we get is that we have the universal property of the Verma that gives us a morphism from the Verma of highest weight lambda to this UV, sending V lambda to V. But
could I
yes,
ask, should
yes.
that, is it possible that that lambda should be mu? Or maybe I'm misunderstanding.
Oh, yes, this one, yes, you're right. Thanks. This is a mu. So we have this morphism, and yes, so this is finite dimensional, this UV. And then by that remark that I made some time ago, we have that because this is finite dimensional, actually that factor, this morphism factors through L tilde mu. But we know by the theorem, the preceding theorem, that this is actually the simple module L mu. Now this is contained in M, and one can easily check that this morphism that we get from L mu to M is the one that makes the sequence split. So this concludes the proof. And also the lecture, I think. So thank you for your attention.
And as I mentioned, attention is easy and giving talks are difficult. So let's thank Leonardo for both of his talks.
Thanks. So I think there were some questions in the chat that I left. So
I answered one. So
okay.
I didn't say correctly what you need to do to get U of G. So so what you need is you take the usual elements, and you also take the element H, well, K minus 1 over V minus 1, or the one that Ivan suggested. It doesn't matter. But what's important, this element is not in the original lattice because it has a denominator of V minus 1. So it's actually a larger lattice, not smaller. And you have to tensor that with C. In other words, reduce modulo V minus 1, and then you get a Q algebra and tensor up with C. And this will give you U of G. And in this operation, this K will specialize to 1 because K is equal to 1 plus V minus 1 times H.
Okay.
All right. Are there any questions?
If we are in a positive characteristic, but still with the Q being, transcendental, do we get semi-simplicity or no?
Well, you get semi-simplicity outside of root of unity.
Okay.
Yeah. Well, for transcendental in particular, yes.
More questions?
Just a comment that I've found it helpful in the past to think about kind of U dot. And then it's much kind of clearer that you can specialize modules that like, is it clear what U dot means?
So
maybe not in this audience.
So this is the Lustig
right.
construction.
Maybe we should discuss U dot at some point.
And we will definitely will.
Okay.
Yeah, U dot is much better for discussing representations.
Yeah. Okay. Are there any questions if I stop the recording?